Good day and welcome to NMC 113. Today we'll actually be looking at metallic crystal structures. In metallic crystal structures we have the simple cubic, FCC, face-centered cubic, body-centered cubic, and hexagonal close packed. There are actually other crystal structures we have, like BCT, which is body-centered tetragonal, but basically mostly the focus in NMC1 is actually the latter three: FCC, BCC, and HCP. And the characteristics of these crystal structures that you need to be familiar with. Characteristics. The first one is the coordination number, which is the nearest touching atoms. And then you determine them by the first thing you do is you choose a reference atom within the unit cell. Choose a reference atom, Secondly, what you do is you count the atoms within the shortest distance from the reference atom. So basically you count the atoms within the shortest distance. From the reference atom you just chosen. Mostly is like within touching distance. Let's just say that the shortest distance is in fact within touching distance. And secondly, another characteristic you need to be familiar with is being able to find the effective number of atoms. The effective number of atoms within a unit cell. And then this constitutes the total number of atoms within a single or within a unit cell. And then the third characteristic we're also going to be looking at is the relationship between the lattice parameter or parameters and the radius, the atomic radius. Radius. Okay, and then fourthly, we're going to you're also going to have to be able to calculate the atomic packing factor. That's the atomic packing factor. It's normally abbreviated as APF, right? And this is the total atomic volume over the unit cell volume. This volume, that total atomic volume, what it means is that it's actually the effective number of atoms, right, multiplied by a volume of a sphere. This is actually what the total atomic volume entails. So as we know that the volume of a sphere is 4/3 pi r cubed. Okay, now we're gonna look at the crystal structures individually, but first let's start with the simple cubic crystal structure. So here we have the unit cell for a simple cubic structure. Now let's actually determine the coordination number. The coordination number for the simple cubic. So now in this unit cell, the first thing I said you do is that you choose a reference atom. You only have corner atoms, so you have to choose one of the corner atoms as your reference atom, and then you look for the nearest touching atoms. So now if you extend this unit cell, there are other surrounding unit cells, because remember, a crystal structure is a sequence, right, of a combination of a number of unit cells. So with that in mind, you know that actually according to this you have another unit cell at the back, right? And then I'm not gonna go draw the entire unit cell, but here you have an atom, right? And then at the top, sorry, just excuse my drawing, it's a bit, squeaky. You have another atom here at the top for the unit cell at the top, right? And then on this side, on the side of this one, you also have another unit cell, right? And then this is the bottom unit cell that you have. You just extend this, right? Now the nearest touching atoms is actually 1 from here to there, to that atom, to this one, that's 2, right? And then from here to this atom is 3, and then the atom at the bottom here, going down here, you have 4, and then this is 5. This is 5. Hopefully you can see, because my drawing pen is quite. This is the 5th one. Let me just erase this. Just find an eraser. Okay, yes. Okay, no, that's much better. Okay, okay, from here to here, right? We said it's 5, it's the 5th one, and then from here to that side, this atom, because it's also touching that atom, it's 6. So you'll see that it's 1, 2, 3, 4, right on this, right on towards this atom. That's 4, and then 5, and then 6. So those are the nearest touching atoms for this particular reference atom, which is a corner atom. So we have a coordination number of 6 in a simple cubic. And then the next thing we do is actually determining the effective number of atoms. So let me just do this. Okay, this is the first thing that we did now. Okay, the second thing, can get the effective number of atoms, right? Now the first thing you have to do is that you also look at what type of atoms you have. What I mean by that is, if you have corner atoms, body-centered atoms, like the orientation of the atom inside the cube. Now you only have corner atoms, right? And then corner atoms have what we call a contribution factor. So you must actually determine the contribution factor of the corner atoms. Those are the only atoms that you have, and then after you determine the contribution factor, you have to actually get the how many atoms are there, right? So you have 8 corner atoms, so a number of corner atoms in this context, you get the number of corner atoms. Or effectively the number of atoms within this unit cell, but we only have like corner atoms, hence I'm using that to delineate to you how to determine the effective number of atoms. So the effective number of atoms, each corner atom has a contribution factor of an 8th, right? And then you have 8 corner atoms, and that means that the total number of atoms within this unit cell is 1 atom per unit cell. And then thirdly, sorry, this looks a bit disorganized, but yeah, just follow the trail. That's it. Thirdly, you determine the relationship. You relate the lattice parameter, right, to the radius. That's atomic radius, right? In this case, if you look at the sketch on this sketch on the left hand side of the stick model, this is a stick model, and then this this sketch here, you can see that these atoms are actually touching each other, and then this is the lattice parameter. This is A. From here to there, it's A. It's just like here, this entire distance here is in fact A, right? And then if you look at this particular drawing, that entire distance there is actually A. Now you can see that this is a full radius. From here to here is a full radius, and then from the next atom towards the edge, it's another radius. So you can actually say that because of that, A, which is the lattice parameter, is equals to 2 radii, right? That's the relationship between the lattice parameter of this cube to the radius. And then now fourthly, you have to determine the atomic packing factor. We say that the atomic packing factor is the total atomic radius, right, within the unit cell and over the unit cell volume. Right? No, sorry, just made a mistake here. Just erase it. This is total atomic volume, not atomic radius. Just excuse that. Okay, let's blow this up. Atomic volume, which is basically just the effective number of atoms, right, multiplied by, let me just say effective number of atoms. I'll just abbreviate effective number of atoms multiplied by sphere volume, right? And this is over the unit cell volume. So we have the effective number of atoms per unit cell. It's 1, right? It's 1 atom per unit cell. Unit cell multiplied by pi. Forgot the 4/3 here. R cubed, right? Over a cubed, because a the lattice parameter, this is a cube, so the volume of a cube, since the parameters are actually just the same, that's actually why we just saying a cubed. And you can write the radius for the bottom, for the denominator, in terms of the radius, using the relationship between the lattice parameter and the radius. So we have 1 multiplied by 4/3 pi r squared cubed, sorry, and then you have 2r cubed, and then the radii is gonna cancel each other, so you're left to 4/3 pi over 8. Let me go down a little bit. I mean, that's the atomic packing factor. If you resolve the equation, it's just gonna give you you're gonna multiply 1/8 with 4/3 pi. That will make it 1/6 pi. That would be your atomic packing factor for the symbol cubic. Okay, there you go. Now let's actually take a look at the face-centered cubic. Now let's take a look at the face-centered cubic. For this particular one, you have body-centered, face-centered atoms on the 6 phases of a structure. So we're also gonna determine what we actually worked out for the simple cubic, which was the coordination number. I said that we choose a reference atom. In this case, like it's much easier choosing the face-centered atoms as your reference atom, because they have when you're making the count, it's actually much easier to make the count when you're choosing the face-centered atom. If you choose a corner atom, you're just gonna make it difficult for yourself, because and some of these atoms, you may not find that it has a as many nearest touching atoms as the face-centered. So for an FCC, choose a reference atom of the face-centered atom. Now if you extend these crystal structure to the right, there's one that has formed into the right hand side, neighboring. Let me just do this. Okay, you have one here, the front, one at the top, and then okay, you have one here, have one at the bottom, and then you have one at the back, and then you have these corner atoms as well. Okay, when you're counting the nearest touching atoms, the atoms is touching this one, right? This one. So it's 1, 2, 3, 4. My lines are not that straight, but as long as you can see. And then it touches the one in the neighboring cell. It's going to be 5, this one, right? And then it's going to be 6. And the one in front, this is going to be 7. Just write 7 here. And then the one at the bottom, which is going to be 8. Pay attention, like if you look at this entire structure, you'll actually see that because of these atoms that are actually touching it, these or the ones on these phases, the one at the phase at the back, this one, it's not going to touch the reference atom we just chose. You don't be able to touch it, therefore we're not counting it. So now we just have 8, and then going to the others, to the our primary cell, the cell that wasn't really extended. You have from here to here, so it's 9, right? To the one at the back, 10. The one at the top, it's 11, right? And then you have one in front, it makes it 12. So the coordination number for an FCC, right? For an FCC, it has a coordination number of 12. I actually hope that you understand this. Most people just cram the coordination numbers because usually you just have, well, you know, a limited number of crystal structures, but it's better to know how to make these calculations so that if they give you a structure you've never seen before, which doesn't happen that often, but you'll actually be able to make the count yourself. And then the second thing here is being able to count the effective number of atoms. Okay. For an FCC, being able to count the effective number of atoms, you have 8 corner atoms, and then like I said, the first thing you do is to actually get the contribution factor, right? My cursor's eluding me. Terribly so. Very terrible. Okay. Contribution factor. Of corner atoms, right? And then the contribution factor. Now we have face-centered atoms as well. Of face-centered atoms. Face-centered atoms. And then after you do that, you actually get how many atoms, number of atoms for each, right? So how many contribution, how many corner atoms are there, and then how many face-centered atoms are there? So that's actually how you get it. And then looking at the structure, you'll just be able to see here. You have 6 phases. 1, 2, 3, 4, 5, and 6. Right. So now you have 6 face-centered atoms, and then the contribution factor is a half, because, like, for example, this one is a half atom. You can see that it's actually part of this unit cell on this. It's part of this unit cell, and it's actually only just half an atom. So the contribution factor of a face-centered atom is a half. So you have for the face-centered, a half, right, contribution, and there's 6 face-centered atoms. And then the corner atoms, the contribution factor is an 1/8, and you have 8 of them. So that makes that FCC has 2 atoms. Sorry, it's 4 atoms. Sorry, it's 4, because half of 6 is 3. You have 4 atoms. Per unit cell. Okay, now the third thing we're gonna be looking at is relating the lattice parameter with atomic radius. Right. If you look to the drawing on the left, or the picture to your left, the leftmost picture, you'll see that here's the radius. This is 2 radii, and this is another radius, and then you have this A here as your lattice parameter. So, and then on this side as well, you have A. Okay, you have A on that side. So for you to be able to relate these, just use Pythagoras theorem. use Pythagoras theorem. It's going to be 4r squared equals to a squared plus a squared, because you have the hypotenuse, adjacent side and the opposite side, and then this would be 16r squared to a squared, and then you have, well, eight r squared, which is equals to a squared. So if you find the square root on both sides, you'll get 2r equals to a. So this is the relationship that the lattice parameter has with your radius, and you'll actually be able to use this relationship when you're calculating the atomic packing factor. So let's just do that. Let's get the atomic packing factor. That's the fourth thing that you need to be able to do, right? Atomic packing factor, and we said that is the total atomic volume within the unit cell and the cell volume, which is a unit cell volume. Okay, we just calculated the effective number of atoms. Let me just rewrite the formula. Effective number of atoms times the volume of a sphere. And then again, unit cell volume. And what we have here is, for an FCC, we have 4 effective number of atoms, right? Atoms per unit cell, and then 4/3 pi r cubed is the volume of a sphere, and then we have a cubed again, because the shape of the unit cell is in a cubic form. And then we can continue to write this so that we write this is 16/3 pi r cubed over 2√2 r cubed. And then the radii cancel each other, right? When the radii cancel each other, you're only left with 16/3 pi over 2√2 cubed. And then you'll use your calculator to calculate the value there. That value should give you the atomic packing factor for an FCC crystal structure. That's it, guys. On the next video, on crystal structures as well, will probably be 30-35 minute video as well. I'll be dealing with the BCC and the HCP.